Hello everyone, today we're going to talk about convolutional neural networks for image denoising. The prerequisites for this material are linear algebra, in particular the singular value decomposition, thresholding, and Wiener filtering. We're going to consider the problem of image denoising, where we have a noisy image and want to estimate a clean image from it. We have already seen two techniques to do this. The first, well actually the last one that we saw, was linear translation invariant estimation, also known as Wiener filtering. The second one was nonlinear estimation. Okay, this one we saw previously when we studied wavelets and short-time Fourier transforms, so maybe I shouldn't say the second one, but anyways. That one was based on thresholding in a transfer domain. So here the idea was that these transforms sparsify the image. They represent the image with a small number of coefficients that concentrate where the signal energy is concentrated on those coefficients. The noise is actually going to be spread out, so by thresholding the coefficients in that particular transform domain, you can eliminate the noise very effectively. Here we're going to present a very powerful denoising technique that combines elements from both. On the one hand, it's nonlinear, just like wavelet thresholding or short-time Fourier transform thresholding. On the other hand, it's translation invariant. Okay, and this technique is based on convolutional neural networks, in particular deep convolutional neural networks, which is why I've written deep learning here. The idea is that you gather a data set of natural images, you simulate noise, and then you train a neural network to estimate the clean image from these noisy images that you obtain by simulating noise and corrupting the images with it, in order to minimize the mean squared error. If we go back to Wiener filtering, this is linear translation invariant estimator, where basically you learn a convolutional filter from data, such that basically here you can see it. We apply the convolutional filter to the noisy measurements to obtain the clean image, an estimate for the clean image. We're going to represent this by a matrix W, which is a circulant matrix. It's equivalent to applying this convolutional filter. We already saw that you can prove that the best filter to denoise signals when the noise is additive and independent is called the Wiener filter, and it does the following. It takes each DFT coefficient and it weights it by the following weights, which are equal to the image variance of the variance of that DFT coefficient across all clean images in your data set of interest, divided by that variance plus the variance of the noise. And this makes a lot of sense, because then if the noise variance is very high, you kill that DFT coefficient. If the noise variance is very low, you preserve it. And that's great. The problem is that you're doing exactly the same thing for every image. And you're using statistics of the DFT coefficients across a large data set. So at the end of the day, what happens in practice is that you realize that high frequency coefficients in images have low variance. They don't contain that much energy. So you end up killing them. Okay, you look at their variance compared to the variance of the noise, and you tend to suppress them. So, and this is because you are actually doing the same thing for every image, so you're just relying on the general statistics. So in particular, if there are some sharp, prominent edges in an image, you're just going to blur them because you're just applying a linear estimate that cannot adapt to that specific image. And that's the main limitation of Wiener filtering. It does something very reasonable, but it does the same thing for every possible image. In order to overcome this limitation, convolutional neural networks essentially apply a more complex model, which is nonlinear and therefore has the flexibility to adapt to each individual image. How is that achieved? Well, we take the measurement X and we apply matrices that contain multiple convolutional filters. Okay, so here basically we would have different convolutional filters within this matrix W1 that would be applied to the measurements. Okay? And so on. Then you take, you concatenate that output and you apply a nonlinearity to it. And this is crucial because without the nonlinearity, you wouldn't be able to adapt to different signals. I'll make a comment about this at the end. The nonlinearity here is very simple. It just looks at whatever goes into it, and each entry that is negative, it just sets it to 0. It's called a rectifying nonlinearity. Once you do that, you apply another set of multiple convolutional filters to what comes out, and again you apply a rectifying nonlinearity. Again, you apply some filters, rectifying nonlinearity for several layers. Okay, this is the penultimate layer. Again, a nonlinearity, and eventually you have a final matrix which again contains convolutional filters, and that collapses the estimate into the right dimensions so that it has the dimensions of the clean image. So we're not going to get very deeply into the structure of convolutional neural networks because it's a bit beyond the scope of the course, but I do want to emphasize that because each of these guys are convolutional, they just contain convolutional filters. They're like block circulant if you want. They have they're equivalent to just taking convolutions with again multiple filters. Because of that, this is translation invariant. Okay, you're doing essentially the same thing to each pixel, but it's a very complicated operation that depends on the actual value of the pixel because of this nonlinearity, and that's absolutely crucial. If you didn't have the nonlinearity there, no matter how many convolutional filters you're applying, you're essentially doing again the same thing, no matter what, like without having some dependence on the input. So the nonlinear part is actually crucial. The second thing I want to point out is that because you have so many parameters, it's not obvious how to optimize this. We usually do it applying stochastic gradient descent, and the form of the nonlinearity, which is just setting things to 0 if they are negative, that nonlinearity is actually pretty good for optimization purposes. Okay, it used to be that neural networks used other things such as sigmoids and so on. For this application, at least, this works very well. Again, there's many details about how to design the architecture of neural networks and how to optimize them and so on, but they're a little bit beyond the scope of the course. What the idea that I want you to keep from this is that we go from having a single linear estimate here, like just a convolutional filter that hits X. This is what we do in Wiener filtering. The way we try to make our method more powerful is by adding more parameters. And the trick here is to apply many multiple convolutional filters, which are all learned from data. But in order for that to be effective, you need to have these nonlinearities so that the corresponding function that you build is indeed able to adapt to each input. Okay, so you have a noisy image. When we apply Wiener filtering, essentially what we're doing is we're again applying, you can imagine Wiener filtering as just averaging each pixel, applying the same average over each pixel, or equivalently as killing the high frequencies, and what happens is that we blur. Wavelet block thresholding is better because it transforms the image into this wavelet domain where things are sparse and they have a certain structure, and we know that the non-zeros are going to be kind of close to each other, so we exploit that to threshold in a smart way, and it does actually significantly better than Wiener filtering. But still, the wavelet transform is not perfect. It's a handcrafted transform, so images are not going to be exactly sparse in that transform. So that is the limitation there. Someone has actually come up with this wavelet transform to try to make images as sparse as possible, but real images are never going to be completely sparse in a wavelet transform. The convolutional neural network actually does significantly better. Okay, and the difference is actually quite remarkable here. These images are not maybe are not very high resolution, but for more high resolution images, it makes a huge difference to apply convolutional neural networks. Convolutional neural networks are the state of the art. Here you can still see a significant difference in how this part is denoised. Okay, it looks really similar to the original one. Wavelet block thresholding has some artifacts there. Wiener filtering just smooths out a lot. So, convolutional neural networks are by far the state of the art for this kind of problems. Okay, so now we're going to try to understand. Again, we're not going to go into a lot of detail, but I do want you to. I want to introduce some analysis based on linear algebra that allows us to at least glimpse at why these algorithms are being so effective. And it's actually related to, and relates them to some extent to this previous methodology that we really understand very well because it's much simpler. Okay, so for a fixed input, we can take the function learned by the neural network, which corresponds to the application. So, I'm not going to go back, but basically it's equivalent to applying all these convolutional filters, then applying the rectifying nonlinearity, then more convolutional filters, then the rectifying nonlinearity again, and so on and so forth. You can take that function and you can do a linearization where this locally for this particular input is essentially equal to a matrix that depends on the input times the actual input. This is just a first order Taylor approximation. It's essentially like taking the derivative if you want, but here of course we don't have a single derivative because the function is mapping a noisy image to a clean estimate. So it's a function from an n-dimensional image to an n times n, dimensional image to an n times n image. But you can still look at all of those derivatives between the entries of the input image and the output image, and that's called a Jacobian. Okay, so without getting into too much detail, basically the Jacobian provides a local approximation where the function, the neural network applied to a specific input, is approximately equal to this matrix, which is called the value, and the Jacobian times the input. Okay, here I'm ignoring the fact that neural networks often have additive parameters because for image denoising, those additive parameters happen to not help very much. And I have a reference about this in the notes. The thing is that now basically we have this super complicated function that is applied to the image, and what we're saying is that this can approximately be seen as, so actually I'm going to vectorize the image, okay? Just to make it simple. So we have this super complicated function that is applied to this vectorized image, and this approximately equal to this matrix applied to the image. And now we can think of the rows of this matrix as filters that are applied to the noisy image in order to denoise. Okay, this is a linear algebraic analysis of what the network is doing, and it's a very local analysis, okay, because this matrix depends on the actual input x. And that's important to point out because this analysis, as we will see, is quite interesting, but it's also limited in the sense that we're only approximating the function very locally. When we look at the entries of this matrix, so here for each pixel, we can approximate the denoised pixel as the inner product between the row of the Jacobian and the noisy image. I'm going to show you what these things look like for a convolutional neural network. So here we have computed the Jacobian, we have the noisy image, which is this vector x here. Okay, so this would be x. And the denoised image is going to be the inner product, the values of the denoised image at different pixels is going to be the inner product between that noisy image and rows in the Jacobian. So this is the first row of the Jacobian. And I want to make very clear what I'm saying. If you take the inner product of this and this, then you get this denoised pixel. Okay? What do we see? Basically this, and that's the result. So it turns out that that denoised pixel is obtained by doing a local average like this, which looks kind of like what a Wiener filter would do. If we look at this other pixel, this pixel is also obtained by doing a local average there, and this pixel is also obtained by doing a local average there. So again, I want to take a step back and make sure that this is clear. What we're saying here is that you can do a linear algebraic analysis of the function learned by a convolutional neural network, and the way you do it is you compute the derivatives of the output with respect to the input, and that tells you that approximately each output pixel is obtained by taking the inner product between the whole noisy image and filters that correspond to the rows of this Jacobian matrix that contains those derivatives. So this pixel here would be the inner product between all of the noisy image and this filter. This pixel there is the result from taking the inner product between the whole noisy image and this filter. This pixel, denoised pixel there, is the result of computing the inner product between the noisy image and this filter here. The cool thing is that these filters adapt to the underlying image structure, because here you can see that the network tries to average but without spilling over the edges. Here the same, it tries to average without spilling over the edges. A Wiener filter would not be able to do that because it essentially applies the same weighted average everywhere, because I mean that's the limitation of the Wiener filter, as we saw before. However, this model, because it contains these non-linearities, is able to adapt and do a different weighted average at different positions. When we increase the noise, remember that when you increase the noise in a Wiener filter, what happens is you average over more pixels, because that's just a reasonable thing to do to try to kill more noise. The neural network does exactly the same thing, except that it actually, is careful about where to average. So if we want to estimate this pixel, we should not average beyond here, because then we're going to blur that edge, and that's exactly what it does. When we're estimating this pixel here, you would want to average, the pixels that are relevant to it, that have a similar value, and the neural network is able to figure out that they are there. Same here. Okay, and if we increase the noise even more, it's very obvious that the neural network is applying adaptive averages that adapt both to the underlying image structure but also to the noise. To the noise, actually, in a very similar way to the Wiener filter, where it tries to average over more pixels if there is more noise, but the crucial difference is that it is able to do that while respecting the underlying structure of the signal. Okay, and again, this is revealed by this very local analysis, which is only valid. So this approximation to the function learned by the neural network is only valid very close to the input image, but still, it shows you how it's adapting. An alternative way of interpreting the Wiener filter, as opposed to just these weighted averages that are applied everywhere around the image, like the same in a convolutional way, is that it's an approximate projection onto low pass 2D sinusoids, because again, we're convolving in the spatial domain. This is the same thing as weighting the Fourier coefficients. The issue is that we weight the Fourier coefficients in the same way for each image. So essentially we kind of kill the high frequencies, so we end up blurring edges and fine scale features. Wavelet thresholding and other sparsity-based denoising methods essentially also implement a projection onto a low-dimensional space. So just to be clear, here this would be a kind of a projection on a low-dimensional space, because you're approximately projecting onto the low frequencies because you kill the high frequencies, because in general they don't have as much energy as the low frequencies. wavelet thresholding can be interpreted as an adaptive projection, because basically you say, okay, I'm going to design these basis functions, or in the case of dictionary learning, I'm going to learn some basis functions that make the image approximately sparse, and then I'm going to project for each different image. I'm going to project onto the basis functions where I see that the coefficients are relatively large. Okay, and that's essentially what thresholding does. So you can see thresholding as an adaptive projection onto the basis functions where you suspect that the image has some actual energy. And the projection is adaptive because you're thresholding. You're basically saying, oh, I'm only going to preserve the coefficients corresponding to the places where I see that the noisy coefficients are sufficiently large. Okay, so you can see wavelet thresholding, or in general sparsity-based denoising methods, as an adaptive projection. Okay, so, and the important thing is that the subsets where you're projecting, as opposed to in Wiener filtering, depends on the input. Okay, so now let's go back to this Jacobian that approximates or to this linear approximation of the function implemented by a neural network. We can compute its SVD, okay? And if we compute its SVD, what we're doing is we're approximating the function first, this linear approximation as the Jacobian, and then if we compute the SVD, basically the function amounts to inner products with the right singular vectors, weighted by the singular values, and then multiplied again by the left singular vectors. So empirically, if we analyze the SVDs of the neural network for different input images, what we observe is that this Jacobian matrix is approximately symmetric. So these U's and V's are very, very similar, like they come in pairs that are very similar. And these singular values, most of them are very small. There's only a few that are large. So this means that we're taking the inner product of X, the input, with a small number, the right singular vectors corresponding to the singular values that are large, with a small number of basis vectors, and then we're multiplying again by the same basis vectors, because again the left and right singular values, the left and right singular vectors are actually similar. This means that the neural network is actually implementing an approximate projection. So this is just a graph showing you the singular values of the Jacobian of a convolutional neural network trained to denoise images for different images. So each blue line is a different image, and what you see is that there's a very small number of pretty large singular values, and the rest are very, very small. Okay, so essentially the neural network is projecting the noisy image onto a small number of basis functions. And when you look at those basis functions, these are the singular vectors corresponding to the large singular values. They essentially look very similar to the image, except that they account for possible perturbations. So if you do a linear combination of these guys, what you end up is with something that looks like the original image, but remember that these of course are computed from the Jacobian of the neural network applied to the noisy image. Okay, these singular vectors that you're projecting on are essentially again an approximation to the underlying image, except that when you sum them, because you see here that they have little edges that are, so here the white part, you can imagine it as positive, and the black part is negative. Essentially, when you add this to the image, what you're doing is you're like moving, in this case, the numbers slightly. This accounts for small shifts or small deformations that could happen in the image. And it means that the neural network has understood that if you just shift the image a little bit, or you deform it a little bit, then it still stays like a clean image. So those are the directions of space in which the network says, I'm not sure, like this could be a valid clean image. So it's essentially doing a projection that takes into account the structure of the images in the training set in this way. Okay. And the point is that when you look at the other directions that are being killed, their essentially random directions. So the neural network is able to identify a subspace of basis functions that look kind of similar to the original image, accounting for possible, perturbations or deformations that are, a characteristic of natural images, and it projects the noisy image onto them. Okay, so this provides another way of interpreting what convolutional neural networks do. In a way, it's doing something similar. Let me go back here. It's doing something similar to what you do with wavelet thresholding, except that it's automatically choosing the basis functions for each individual image. Okay, that's the point at which I wanted to get. It's nonlinear, it's adaptive, like wavelet thresholding, but it's also adaptive in terms of the basis functions that are being used, which is why it is much more flexible than wavelet thresholding, and it ends up achieving better results. Okay, so, I know that I'm kind of making a lot of statements about neural networks that might sound a little bit mysterious. Part of it is because a lot of this is intuition, so it is very important to develop more tools to analyze these methods. And part of it is because it's a little bit beyond the scope of the course to get into the nitty-gritty of the details. But let's see what we have learned. We have learned that convolutional neural networks are nonlinear translation invariant models. So you can think of them as a Wiener filter, which is much more complicated and incorporates nonlinearity so that it can actually adapt better to each individual signal. When we do an analysis of the Jacobian, we see that we can interpret the neural network, at least locally, as learning adaptive filters that respect the image structure while adapting also to the noise, trying to average over more and more pixels when we have higher noise levels. Or this other analysis of the Jacobian based on the singular value decomposition, allows us to interpret what the neural network is doing as projecting the noisy signal onto a low-dimensional subspace that is completely adapted to the image. And it does not have to be designed previously, okay? Because again, and it's important to emphasize this, these models are completely learned from the data. You just say learn like many multiple convolutional filters. You apply these nonlinearities in between. It's completely data driven. You just minimize mean squared error and you end up with this highly complex model. It turns out that when we analyze it using the Jacobian, it makes quite a lot of sense, but still it's a very complex model. And I do want to emphasize that many of the properties of this model are not well understood, and very exciting research is being done in this direction. Thank you very much.